Hello everyone, welcome back to the channel. So in the previous session we have completed regarding preparation of colloidal solutions. Now in this session we go for the next concept, that is properties of a colloidal solutions or colloidal source. So in the previous sessions, yes, we have completed preparation as well as purification of colloidal solutions. Now we are going to think of the continuous part of the chapter, that is properties of a colloidal solutions. Well, when you think of properties, yes, we can list out various properties for a colloidal particles, or I can say colloidal solutions. One among them is the colligative properties. Yes, the colloidal solutions or colloidal particles also exhibit a colligative properties. Well, here the meaning of colligative properties, we should understand the meaning of colligative properties. Yes, here what is colligative properties means, yes, we say in chemistry we have already come across the term, that is while dealing with a chapter called solutions. There we studied meaning of colligative properties, and even we have listed out the all colligative properties and we studied in detail one by one. Yes, so in overall what I can say here is colligative properties, first thing to be remembered is colligative properties are the properties of a dilute solutions. What we say, colligative properties are the properties of a dilute solutions. Further, it depends on what? It depends on number of particles. It depends on the number of particles, but not on their nature. So what we say in chemistry, the colligative properties are the properties of a solutions. What type of solution? Dilute solutions. Properties of a dilute solution that depends on the ratio of number of solute particles and number of solvent molecules in a solution. But what they not on the type of chemical properties present. So overall what we say is colligative properties are the properties of a dilute solutions. It depends on the number of particles, but not on their, not on its nature. Okay, well, yes, how many colligative properties are present? Yes, we can say there are how many types? There are four types of colligative properties present, right? Say we have listed out all those four properties. Well, one among them is osmotic pressure. So osmotic pressure is a one of the colligative property. Yes, just we recall in brief, what is osmotic pressure? Is an minimum external pressure. So is a minimum external pressure where we apply, which is applied on the solution surface. The minimum external pressure applied on a solution surface for what? Just to stop a phenomenon called osmosis. Okay, so remember, osmotic pressure is nothing but is the minimum external pressure applied on a solution surface just to prevent osmosis is called osmotic pressure of a solution. Okay, well, here we said to prevent osmosis, then we should be aware about osmosis meaning. So what is osmosis? It is the flow of solvent molecules through semi-permeable membrane from what? From dilute solution to concentrated solutions. So here what happens, there will be flow of solvent molecules takes place through what? Through semi-permeable membrane. Solvent molecules pass through semi-permeable membrane from what? From dilute solution, to what? Concentrated solution. So here meaning dilute solution means, say, solute, we know that solute and solvent present in a solution. So dilute solution meaning solute particles are present in less in quantity while solvent particles are present more in quantity. Okay, on the other hand we said concentrated solution meaning opposite. Solute particles they present more in quantity, and what about solvent particles present in. What happens, solvent molecules move from its higher concentration to its lower concentration, or simply we can say movement of solvent molecules from dilute solution to concentrated solution through what? Through semi-permeable membrane is called osmosis. Okay. So to prevent this osmosis, we have to apply external pressure. Whatever the pressure we apply is called osmotic pressure. So it's one of the colligative property. It depends on what again? It depends on the number of particles. Okay. Well, similarly, see here we said semi-permeable membrane. What is that? Semi-permeable membrane means the membrane which is permeable to solvent molecules but not a solute particles. Why we are saying semi-permeable? Semi means partially permeable. Okay, which allows only one kind of particles, or I can say selective particles, to pass through. So here semi-permeable membrane, that membrane which is permeable to what? Permeable to solvent molecules but not a solid particles. Well, now we go for second colligative property. It is the lowering in vapor pressure. So first one osmotic pressure and the second one lowering in vapor pressure. Yes. So if we consider lowering in vapor pressure means it is the reduction in the saturated vapor pressure of a pure liquid when solute is introduced. So we already discussed in detail. So just we recall things. What we say, it is the decrease in the okay decrease in the vapor pressure, or we can say reduction in the saturated vapor pressure of a pure liquid when solute is introduced. So it is the lowering in vapor pressure. So if we consider lowering of vapor pressures, let's say okay, P naught. P naught is the vapor pressure of a pure solvent, and P is the vapor pressure of solution. Now, when solute is added to solvent, what happens? There is a vapor pressure decreases, which means I can say P naught is greater than P. When solute is added, vapor pressure decreases. So P naught, it is the vapor pressure of solvent, and P means it is the vapor pressure of a solution. So always there will be vapor pressure of solvent is greater or more than vapor pressure of its solution. So this difference what is the difference? P naught minus P. So this difference is the lowering of vapor pressure. Okay, lowering of vapor pressure. Further, we consider relative lowering of vapor pressure. What is the thing? Relative lowering of vapor pressure. Relative lowering of vapor pressure is nothing but it is the ratio. It is the ratio of lowering of vapor pressure to the vapor pressure of a pure solvent. So what is the ratio we are considering? Say P naught minus P is nothing but lowering of vapor pressure. Okay, P naught is the vapor pressure of a pure solvent. So this ratio is the relative lowering of vapor pressure. So I repeat, the ratio of lowering of vapor pressure to the vapor pressure of a pure solvent is called relative lowering of vapor pressure. So this relative lowering of vapor pressure is also one of the colligative property. Okay, well, now coming to the next one, depression in freezing point. Okay, we know the freezing point meaning. Yes, so depression in freezing point means, yes, here also what happens. So whenever a solute is added to solvent, what happens? It describes the process in which addition of solute to solvent decreases the freezing point of a solvent. So whenever a solute is added to solvent, what happens? Its freezing point decreases. So we call it is the depression in freezing point. Well, the next thing, elevation in boiling point. So again, as like depression freezing point, what happens? It describes the phenomenon that the boiling point of a liquid will be higher when compared to its solvent, or else I can say whenever a solute is added to solvent, boiling point increases. Therefore we say elevation in the boiling point. So overall, what we can conclude here, say the colligative properties, all colligative properties depends on what? It depends on the number of particles, the ratio of number of solute particles and number of solvent particles. So larger the particles, more is the value for colligative property. Less the number of particles, less is the magnitude of a colligative property. Okay, well, now here coming to the colloidal solutions or colloidal particles. Now, colloidal particles are big aggregates compared to the particles in a true solutions. So, whenever if we consider size of the particle, we already said here, if the size is less than 1 nanometer, it constitutes what? It constitutes the, okay, crystalloids. It constitutes the crystalloids, or even I can say true solution particles. Further, if size is in the range of 1 nanometer to 1000 nanometer, it constitutes the colloids. Yes or no? Therefore, we say when on comparison, on if we compare the size of the particle, whose size is more? Yes, colloidal particles are going to have larger size compared to crystalloids, or I can say true solution particles. Therefore, what I am saying here, the colloidal particles are big aggregates. They are having large size compared to what? Compared to particles in a true solution, or I can say crystalloids. Yes. Now, to observe, now we have to observe the particles size, or you can say particles of a colloidal solutions and a true solutions. So whenever if you look at these diagrams, so what we are analyzing, colloidal particles. In the first vessel, colloidal particles are immersed. In the second vessel, we placed a true solution particles. Now on comparison, size of the colloidal particles is greater compared to true solution particles. And even if you think of number also, where the number is more, in true solutions, there will be large number of particles, while in colloidal solutions, there will be less number of particles. Okay. Therefore, what we can conclude here, say in true solutions, as we observed in the diagram, true solutions are going to have a large number of particles compared to what? Compared to colloidal solutions. Now we can see here, so we can conclude that number of particles in a colloidal solution is less. Okay, number of particles in a colloidal solution is less and than the number of particles in a true solutions, that we can observe here. Now we know that, what about colligative properties? Say, for a given number of solvent molecules, colligative properties are directly proportional to number of solute particles. Means, if solute particles are more, what about colligative property? Its value is also more. So, hence, what is the conclusion we can draw for the value of colligative properties is of small order. Okay, on comparison with the true solutions, the value of colligative properties of small order as compared to the value of true solutions. Okay, when on comparison, if you compare the colligative properties of a colloidal solutions and true solutions, usually what happens, the value for colligative properties will be small order, its value will be very low compared to true solutions at a same concentration. If you consider true solutions and colloidal solutions at same concentration and having same number of solvent molecules, okay, so the colligative properties of colloidal solution will be less compared to true solutions. Okay, it's regarding the first property, that is, what is that? Colligative properties of a colloidal particles will be less compared to true solutions. It is the conclusion we have drawn. Now, before going for the second property of a colloidal solutions, let me go through certain analogy. Say, yes, we have seen a projectors which are fixed in a cinema hall, right? Yes, visit the cinema hall and even we can see that projector path. Yes, we are observe, right? So we observe like this, whatever the diagram we are showing here, so we observe a projector path in a cinema hall, which is clearly observed, right? Even we can think of a small slit, if there is a small slit or small opening in our house, okay, at the roof, if light enters through that slit, we can observe a projector path, right? We can observe that path of a light clearly. So it is nothing but it is the scattering of light beam. Okay, it is the scattering of light beam. Light with help of projector. What we observe is if image is observed on a screen, right? So when you pass the light through projector, a clear image is observed on a projector screen. It is due to why it happens means it is because of a Tyndall effect. Okay, whatever the things we observe, say in cinema hall, okay, in cinema hall we observe projector path. Okay, not necessarily cinema hall. In general, a projector path can be clearly observed, and a slit. If there is a slit at the roof of a home, say whenever light enters through this slit, even we can observe a clear path of a light, right? Yes, it is because of what? It is because of a Tyndall effect. Why we are observing a projector path means it is because of a Tyndall effect. Yes. So what is this Tyndall effect? Say the Tyndall effect is due to the fact that colloidal particles scatter light in all directions in a space. So first remember Tyndall effect. Tyndall effect is due to what is it called? It is due to scattering. Okay, scattering of light. Okay, scattering of light by what? By colloidal particles. Okay, please remember what we can analyze here, that a Tyndall effect is nothing but it is the scattering of light by colloidal particles in all directions in a space. So why we observe Tyndall effect means it is because of scattering of light by colloidal particles in a all directions. Yes, how they going to scatter the light? Say before going for that, we just analyze certain things. Consider true solutions. We know the meaning of true solutions here. So it is a homogeneous mixture of two or more components. So true solutions, we have taken a true solutions. Now say it is placed in a dark room, and whenever a light is passed with the help of light source, whenever a light is passed through true solutions, light radiations are allowed to pass through these true solutions. Okay, yes, what happens, what we can analyze here means a light source appears clear in the direction of a light beam. So it is the direction of a light beam. Light travels in all directions. Now it is the direction of a light beam. So whenever we analyze through these true solutions, what we observe, light source appears clear. It appears clear in the direction of a light beam. If you consider, if you along with the path, what we observe, which appears clear. Okay. Now, what is the angle here? If we consider it is a beam path. Now, what is the angle here? Right angle means 90 degree. Okay, 90 degree. So perfectly dark. How it appears if you look at from the top side, or I can say at right angle to the direction of a, it is the direction of a light beam. Now we are observing from top. Okay, top view. So what is the angle here? 90 degree. Okay, therefore I said perfectly dark from a direction at a right angle to the direction of a light beam. Okay, so if you observe along the path, okay, in the path direction of light beam, how it appears clear. Okay, it appears clear, but it appears dark when, if you observe at right angles to the direction of a source, the light beam. Now whenever, if you use true solutions, what we are observing, please recall the observations. Along a, or you can see in the direction of light beam, it appears clear. Okay, light source appears clear in the direction of a light beam, but it appears dark. Okay, it appears dark from the direction at right angle to the direction of a light beam. Okay, well, now the same thing, Now we are going to replace it at the place of true solutions. What we are going to place? We are going to take a colloidal solutions. We know the meaning of a colloidal solutions. Yes. Now what we observe when we take a colloidal solution means, say again, when we observe along the or in the direction of a light source, again same direction. If you observe in the same direction, in the direction of a light source, how that it appears translucent. So in true solutions it appears clear. Okay, it appears clear. Okay, but in case of colloidal solutions, light source appears translucent translucent in the direction of a light. And again, what is the second observation we made? At right angles, to the, okay, path of a light beam. So when viewed at right angles to the direction of light, it shows mild to strong opalescence. Okay, so there is a difference. Now if in case of true solutions it appears dark, right? It appears dark at right angles, but in case of colloidal solutions it appears opalescence. Means there's a difference in the observations. Well, here say we have taken colloidal solutions with the help of light source. Whenever light is allowed to pass through the colloidal solutions, what we observe is, say, scattering of light get scattered. Whenever, say, light source hit the colloidal particle, what happens? Part of the light is absorbed and remaining will be get scattered in all directions. So we say the scattering of light beam is due to the fact that soul particles absorb light energy and then emit in all directions in a space. So say if I consider it is a soul particle, say whenever light radiation hit the soul particle, what happens? It part of the radiation is absorbed. Okay, part of the radiation is absorbed and remaining is get okay, scattered in all directions. So we say soul particles absorb light energy and then emit it in all directions. Therefore we observe scattering of light. This phenomenon is considered as a Tyndall effect. Okay, well, now, the Tyndall effect, we already mentioned, the Tyndall effect is due to the fact that colloidal particles scatter the light in all directions in a space. Okay, well, now who is observed for the first time? This fact, this effect was observed by Michael Faraday. Okay, but this phenomenon is studied by Tyndall. Hence, it is named as a, or it is termed as a Tyndall effect. Okay, for the first time, that study was begun by Michael Faraday, but in detail studied by John Tyndall. Hence, it is named as a Tyndall effect. Okay, well, if we consider conditions, what are the conditions to observe Tyndall effect? Means Tyndall effect is observed only when two conditions are fulfilled. Yes, the first one, the diameter of the dispersed phase particles. It must be, okay, not much smaller than the wavelength of light used. So what we are comparing? We are comparing diameter. We are comparing the diameter of dispersed phase particles with the wavelength of light radiation used. The diameter of a particle is not much smaller than the wavelength of light used. Then the second one, the refractive indices of dispersed phase and medium, dispersion medium, they must differ greatly in magnitude. Okay, there must be large difference between refractive indices of dispersed phase and refractive indices of dispersion medium. There must be a large difference between these two quantities, that is refractive indices of dispersed phase and dispersion medium, they must differ greatly. Okay, well, so these are the two conditions must be fulfilled to observe a Tyndall effect. First one, the diameter of the dispersed phase particle, diameter of a dispersed phase particle should not be smaller, not much smaller than the wavelength of light radiation used. Okay. And second one, the refractive indices of dispersed phase and dispersion medium, they differ largely. Okay. If these two conditions are fulfilled, we can easily observe the Tyndall effect. Okay. Well, now here I said refractive indices. So what it is? That refractive indices is the ratio. Okay. It is a ratio between what? Ratio of velocity of light. It is the ratio of velocity of light in vacuum to the velocity in a specific medium. Okay. Yes. Now, Tyndall effect. What is the use of this Tyndall effect means? Yes, Tyndall effect is used to distinguish between colloidal solutions and true solutions. So, true solutions, they do not show Tyndall effect, but colloidal solutions, they show Tyndall effect. Means, yes, it is used. Okay. What is the application of a Tyndall effect? Where we use means it is just used to distinguish. It is used to distinguish between colloidal solutions and true solutions. Okay. Well, now add to your knowledge, in 1903 sigmoid used Tyndall effect to set up apparatus known as ultramicroscope. Okay. So in the setup of ultramicroscope, the knowledge of Tyndall effect is used by whose scientist? Sigmoid. Okay. Well, now how it helped to in the setup means he experimented on colloidal solutions which was placed in a glass vessel. He took a glass vessel in which he took a colloidal solutions. An intense beam of light is focused on a colloidal solutions and observed with a microscope at right angle to the beam. So what here Richard done here? He took a colloidal solutions in a glass vessel and an intense beam of light is focused on it and observed at right angles to the path of a beam. So yes, the individual colloidal particles, okay, what he observed in microscope means that individual colloidal particles appeared as a bright stars. How they appearing? They appeared as a bright stars against a dark background. So in a microscope, ultra microscope, what he observed, all the colloidal particles appeared in the as a bright stars against a dark background. Then if you think of that, ultra microscope is not going to provide any information about size or shape of the colloidal particle. What he observed, he just observed that light scattered by them. Okay, light particles are only scattered by those colloidal particles. Why they are appearing star like means it is because of scattering of light. That light is get scattered by those particles. Okay, but is not going to get any information regarding what size of the particles and even shape of the colloidal particles, but only help to observe light scattered by those colloidal particles. Okay. Yes. Now coming to the MCQ, the first one, colligative properties depends on. It depends on what? It depends on the number of solute particles, number of solvent particles, type of chemical species, and the fourth one A and B. Yes, what is the answer? It depends on the ratio of number of solute and solvent particles. Means option A and B. Now, second one, colligative properties among these. Osmotic pressure, okay, a relative lowering, actually it is the relative lowering of vapor pressure, depression in freezing point, and all of the above. Yes, all are colligative properties itself. Okay. Yes. So with this, I'm going to conclude about this session. Again, in the next session, we continue the rest of the part. Okay. Thank you. Be safe.
Yeah.